Hello everybody and welcome back to another Big Ideas lesson. Today we're going to be discussing lesson 8.1. We are starting Unit 8. Now, Unit 8 is all about graphing. So you are absolutely going to need some graph paper. For today's lesson in particular, you are going to be using a whole sheet of graph paper. So please feel free to split it in half twice to make a 4-quadrant coordinate plane. Before we use that, though, I want us to talk a little bit and review a little bit about what we've done with graphing. So with graphing, we've learned to graph a couple of things. We've learned to graph, for instance, y equals mx plus b, where m is the slope and b is the y-intercept. And we called this a linear function. And when something is linear, it makes a straight line. So we know how to do that. We've also learned another form. We've learned y equals ab to the x, where a is your y-intercept and b is your growth factor. This was our exponential. And the exponential, when we graphed it, looks like a curve, something like this. Today, we are going to be learning the third one. But I'm only going to tell you the name. I'm not going to tell you the equation. I'm not going to tell you what it looks like. That's what we're going to be doing together. The one we're learning today is called a quadratic function. I'm not going to tell you what the equation is just yet, and I'm not going to tell you what it looks like. That's what we're going to figure out together. So let's do this. I want to figure out what the graph of y equals x squared will look like. Do we know what this graph is going to look like just by staring at the equation? Probably not. In general, you're going to see a lot of equations that you won't know exactly what it looks like. You won't be able to say, pick out a point and pick out what it's going to look like and then just immediately graph the whole thing. Instead, we have to use a strategy for when we come across an unknown function. The strategy that I always recommend is anytime you come across a function you don't know what it's going to look like, make a table and figure out what the inputs and outputs will be like. So here's what I want us to do for today. I want us to use 9 inputs and get 9 outputs. 9 dots seems like enough to see what a graph is going to look like. The 9 inputs I'd like us to use are -4, -3, -2, -1, 0, 1, 2, 3, and 4. So let's talk about this. Let's talk about how to do this. We've made a list of x values. And of course, you could use any numbers you want. These are just nice because they're smaller and because we get some on the negative side, some on the positive side. When you make a table, in general, if you can, you want to see if you can get some negative and some positive values. We'll learn in this unit that's not always going to work, but in general, that's sort of our goal. We want to see what the whole graph looks like. But if we know the x values, how do we figure out our y values? Well, this is where we remember our equation. Our equation is that y will equal x squared. The thing we're looking for is equal to x squared. So if we really wanted to find any of these values, let's say we wanted to find the value of 3 here, all we would need to do is plug 3 in to the equation. Y equals, instead of x squared, it would be 3 squared. And in general, especially in this unit, it's very important to put parentheses around whatever term you are inserting, whatever term you're substituting in. Well, what is 3 squared? We know what 3 squared is. 3 squared is 9. So y equals 9. What we've just done is we have made a point. Oops, sorry about that, everyone. We found that the x value is 3, the y value is 9, so we've made the point 3, 9. On the back side of this paper where our graph is, we can actually now label it with that point. We can go over 1, 2, 3, and up 1, 2, 3, 4, 5, 6, 7, 8, 9. And we get a dot right here. That's one of our points on our graph. Here's what I want you to do. I want you to pause this video, and I want you to try to fill in all of the missing values of y. There are 8 more that we're trying to find. Once you find your missing values, figure out what point that corresponds to, and then graph it. We'll discuss in a minute. So for now, pause the video and try it out. How'd you do? We should have gotten the following. Negative 4 squared is 16, negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. So these are the points we get. A quick word about this. You may have noticed that all of our negative numbers turn into positive numbers. We talked about this difference before, but there is a huge difference between, for instance, negative 3 squared and negative 3 squared. The bottom one, negative 3 squared, is negative 3, because that's the quantity being squared, times negative 3. And a negative times a negative is a positive, gives us 9. Negative 3 squared is the same as, hey, what's the negative version of 3 times 3? Well, that's just 9, so it's negative 9. Be very careful. That's why we want to use parentheses. We want to have these parentheses around whatever we're inserting. So when we graphed it, we should have gotten this arrangement of dots. Let me zoom out again. This arrangement of dots. Well, what are some things we notice about this arrangement of dots? You may have noticed that it sort of forms a bit of like a U or a V. Additionally, you may notice that it's the same on both sides. These 2 points match up, these 2 points match up, these 2 match up, these 2 match up, and then we have our middle point. Let's complete the shape. To complete this shape, we want to draw a smooth line going from one side to the other. Keep in mind that this U shape or V shape got steeper over time. So while it's never going to go straight up, it got very close there near the end to going like straight up. There we go. It's going to be a little rough there in the middle, but I think we nailed it. And because it keeps on going up, we can draw these 2 arrows. So it makes a shape kind of like this. Kind of like a blend between a U and a V, although it's a little bit squiggly there in some parts. This is the shape of a quadratic. This shape is called a parabola. Yes, you heard me correctly. Parabola. It is spelled P-A-R-A-B-O-L-A. A parabola is sort of this weird U-V hybrid. Like it looks kind of like a U, but then it dips down to like a much more pointy spot. It's a parabola. So this is actually the shape of a quadratic. Quadratics, when you graph them, make parabolas. Sort of like this U and a V hybrid. With parabolas, there's a couple very important parts. For starters, let's take a look down here at the very bottom. You see this little dot where the parabola changes directions? This little dot is called the vertex. The vertex is the spot where the parabola changes directions. You can think of it as the bottom of a parabola, or if our parabola was flipped upside down, it would be the top. So the vertex is where the parabola sort of changes directions. And what coordinates does this vertex have? Well, it has the coordinates at 0, 0. It's at the origin. So our vertex is 0, 0. Very nice. Remember how I said that this parabola looks the same on either side? Like if I cover up the right side, it looks the same as the left side, just flipped over the y-axis. We call the line that the parabola flips over something called the axis of symmetry, because it's, well, symmetrical on both sides. This is going to be your axis of symmetry. Let me write this down. Axis of symmetry. You'll see me abbreviate it as AOS in the future. The axis of symmetry is that line over which your graph flips. Like you can imagine, if I was to fold this paper in half, you can see that the graph sort of flips over this folded line. See how it almost matches up perfectly as we get in close together? So the axis of symmetry is where it flips. We want to write the axis of symmetry as the equation of a line, since that's really what it is. It's a vertical line. We have to look back at Unit 3. In Unit 3, we learned that the equation of a vertical line is x equals whatever x value that line is going through. And what's the x value of this line? All these points go through x equals 0. So our axis of symmetry is x equals 0. There's a couple more things we like to talk about when we talk about parabolas. We do want to look at the domain and the range. And I know this one, a lot of people mentioned they did not like. It's okay though, we'll review it. The domain and range are just fancy words for saying how wide the line can go, like how far to the left and how far to the right it goes, as well as how tall it can get, the highest and lowest points. But this parabola sort of continues on, and it gets wider and slightly wider and slightly more wide. Do you think it's ever going to stop going to the left and right? Do you ever think it's going to go straight up and never get wider? The answer is no, because you can always plug in another x value. Like let's say, for instance, we plugged in x equals 6, 7, 8, 9, 10. Even if we plugged in a point like x equals 10, the parabola will still have a solution, because this parabola is given by the equation y equals x squared. As long as x has a square, does 10 have a way to square it? Well, yes, that'll give you 100. As long as you can still plug in values of x, your domain will exist. So the domain works for all numbers, because you can square any number, really. This is interesting. It means that our parabola is never going to stop going to the left and right. Its domain is all real numbers. You may also see me use this symbol throughout the unit. It's an R with like an extra little leg on the side. It's technically supposed to be a bolded R. This is the symbol for all real numbers. So you might see me use that in its place. The range is a lot like the domain. It's trying to figure out how high up or low down the graph can get. But this time, is there a restriction to how high or low it gets? Well, it's always going to keep going up, but does our graph ever dip into the negatives? No, it has a lowest point. Our range is that the y value can be anything as long as it's bigger than 0. So the range is y is greater than or equal to 0. Next up, we want to talk about how this graph is changing. Let's take a look at it as we go from left to right. As we go from left to right, notice the direction it's sort of going. It starts to go down a little bit. Notice how it starts to go down towards this vertex. We say that that's where it is decreasing. But then, after it hits 0, it goes back up again. It starts increasing once again. We will also want to discuss where our parabola is decreasing and increasing. We also want to be able to point out where the parabola is decreasing and increasing. Well, it's decreasing everywhere below or to the left of this middle point. And where is this middle point? Well, it's at 0. So our parabola is decreasing up until it gets to 0. When x is less than 0, it's decreasing. At 0, we say it's not really decreasing or increasing. It's just there at the bottom. Finally, after we hit 0, it starts going up again. So we would say that it's increasing when x is greater than 0. There is one more thing we talk about called the characteristics, but we're not going to talk about that right now. We're not going to talk about the characteristics right now because there's nothing really special about this graph. Very nice. This is what you're expected to be able to list off. And it looks like it's a lot, but really, you can kind of catch a lot of these at a glance. The vertex, bam, right there. The axis of symmetry, bam, right through the vertex. The domain of our parabolas, as long as they're up and down, will always be all real numbers. The range is always going to be related to where our vertex is. It's decreasing sometimes before the vertex, sometimes after the vertex. It's increasing sometimes before the vertex, sometimes after the vertex. And we'll talk about characteristics in a little bit. First, I want us to take a look at our student journal on page 247. On page 247, we're finally going to solve some of the mysteries of our parabolas. First things first, we talked about how all of these have equations, and I think it's time we talk about the equation of a quadratic. The equation of a quadratic may look very familiar. It's ax squared plus bx plus c. This is a quadratic function. In fact, let me write this down in our notes. Our quadratic function is y equals ax squared plus bx plus c. Doesn't this look familiar? This is the equation of a trinomial from last unit. Quadratics and trinomials are basically the same thing, just different ways of interpreting it. Also, quadratics will be in different forms, as we can find out soon. But a quadratic function is just y equals ax squared plus bx plus c. Just to let you know, for this unit, we're only going to be looking at what happens when we have ax squared. We're imagining that b is 0 and c is 0, so they cancel out. In 8.2, we'll add on our c value and see how that changes our graph. In 8.3, we'll add in our bx and see how that changes the graph. The parabola is just this U shape that we discussed before. It's the U shape of a quadratic. The vertex is going to be either lowest or highest point on a parabola. We could think of it as the place where the parabola changes directions, from decreasing to increasing or increasing to decreasing. Last but most certainly not least, we have the axis of symmetry. And the axis of symmetry is the vertical line that cuts our parabola in two. It's that vertical line that cuts our parabola in two. And if you ever need to see what we just talked about on the seed paper, it's basically all right here, just in a much more neat form. All right, like I mentioned, we have a quadratic equation here. But we're not going to talk about the bx or the c. But we haven't talked about our a value. That's something that we have neglected to talk about. Let's change that. On the back of your paper, of your graph paper, once again, we are going to make two more quick tables. I want us to try to see what happens when our a value is 2, so we have 2x squared. And again, I want us to make a table of values using the same numbers we did as last time. So -4, -3, -2, blah, 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 just like the ones over here. I also want us to try out what happens when our a value is a fraction. So when we have y equals 1/2 x squared. -4, -3, -2, blah, 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 blah. Fill in these tables. Try to figure out exactly what they look like on a graph and graph them on the same graph as this. Take a minute, try it out, and pause the video. How'd you do? As we look at these different answers, we might see a pattern start to emerge. Let's take a look at the 1/2 side. In the original, we got 16. In the 1/2 side, we got 8. In the original, we got 9. In the 1/2 side, we got 4.5. On the original, we got 4. On the 1/2 side, we got 2. By having a 1/2 in front of the x squared, it's basically going to cut all of our y values in half, meaning they're only going to travel half as far up the graph. And the opposite is true of the 2x squared. In 2x squared, we're multiplying everything by 2. So everything goes up so much faster. I did graph these on my graph here, but I was not content with how messy it looked. So what I've done is I've also printed off a version of these graphs. It's a little bit smaller, but we can sort of see the important bits here. Let's take a look. Our original graph is right in the middle. I'm going to highlight our original graph in orange. The graph of 1/2 x squared was this one. I'm going to highlight this one in blue. And the graph of 2x squared is right here. I'm going to highlight that in yellow. What's the same about all three of these graphs? What did adding an a value not change? Well, let's do our analysis. We always want to take a look at a couple of things. Did the vertex change? Nope. Vertex is still right there. Vertex is the same. Our axis of symmetry, our AOS. Nope. Still right down the middle, still at x equals 0. So that's fine. The domain and range, both the same. The lowest point is still 0, but it goes up to infinity. And these graphs are always going to get wider and wider and wider. Domain and range is the same. Increasing and decreasing, still the same. It's still decreasing on the left and increasing on the right. So what really did change here? It's that last piece that we didn't get a chance to talk about, something that we are going to call the characteristic. Characteristics. The characteristics describe how a graph transforms from the parent function. The parent function is the one without any modifications. So in this case, our parent function is y equals x squared. Y equals x squared, our orange, is our parent function. But that parent function changed here by adding a 2 in front, or multiplying by 2, I should say, and here by multiplying by 1/2 in front. By transforming the parent function, you can get different versions of the graph. And this is where the characteristics come in. Let's take a look at the yellow. What happened to this yellow graph? How did it transform? Well, our yellow graph, y equals 2x squared, got smaller. It got narrower. It got almost like it was pulled up a little bit. What happened to y equals 1/2 x squared? It got wider. This is something very interesting about the characteristics of a quadratic. It doesn't just apply to quadratics, but we're going to be looking at it in the context of a quadratic right now. If you have an a value that is bigger than 1, our parent function was 1, 2 is bigger than 1, if your parent function has an a value that is bigger than 1, it gets narrower. If we have an a value that's in between 0 and 1, such as our fraction 1/2, it's going to get wider. So our a value changes how wide or narrow our graph is, but it keeps everything else the same. All it does makes our graph wider or narrower. We don't want to use the words wider or narrower, though. We have two very specific ways of describing these. To imagine the following, or to describe these, I want you to imagine the following. Imagine that our graph is a rubber band, and I'm putting my finger down at the vertex. And I pull and stretch the rubber band. What happens? Well, the rubber band is going to get skinnier and skinnier and skinnier as I keep pulling on it. As I keep pulling the rubber band out, it gets skinnier and skinnier. This is why it gets narrower. We call this pulling of the rubber band, we call this, where it makes the graph skinnier, a vertical stretch. Vertical stretch. That's the characteristic. The characteristic is, for y equals 2x squared, we have a vertical stretch. As it gets wider, imagine we're taking that rubber band from all the way up here, and we're sort of pushing it back to where it started. The rubber band would get wider and wider and wider. We call this then a vertical shrink when it gets wider. It seems counterintuitive that a stretch is where it gets narrower and a shrink is where it gets wider. But think of it as pulling a rubber band and pushing that rubber band back together. That's really what we're doing here. So, when our a value is bigger than 1, it gets a vertical stretch, it gets narrower. When our a value is in between 0 and 1, we have a vertical shrink. Here's a question for you. What do you think is going to happen when our a value is less than 0? When our a value is negative? To answer this question, I recommend you do the following. Make one last table. Make one last table. Use the same values we have been using. I'm just going to make this table sideways for space reasons. Use the same values we have been using and graph it. See what happens when you graph y equals, and we make our a value negative, it would be negative x squared. Try this out and see what you get. Pause the video here one last time. How'd you do? You should have noticed that it's the same as x squared, but all of our y values are negative, so the graph turned into an upside-down parabola. In this parabola, everything is going to be the same except for our range. Instead of y being bigger than 0, it's going to be y is less than 0. Our y values are all negative, so they're less than 0. Instead of it decreasing when x is less than 0, it's increasing when x is less than 0. and then decreasing after we hit x equals 0. We do have one more characteristic that we're going to call this. I like to call it a flip. I like to personally just call it a flip. It's easy to remember, but Big Ideas is going to word it a little bit differently. They call this flip a reflection in the x-axis. A reflection in the x-axis. A reflection in the x-axis basically just means, hey, imagine that we're flipping our graph over the x-axis. It would turn upside down. When you see that you have to list off a characteristic, these are the characteristics you are looking to list. With that said, everybody, thank you so much for listening. Try out the practice. See if you can identify these characteristics of our parabolas. I will catch you next time.